Hi, hello everybody. This is Dr. Tracy Tooth from Sac State. We're here to do a quick lecture on EEE 145, Chapter 0, Power Engineering Review. All right, so here we have Ohm's Law. So Ohm's Law is very basic. V equals I times R. I typically see V as a voltage source or a generator. R is your load, like your house, and you just want find how much current is flowing from the generator to the load or your house. Okay. Next, as power engineering says, calculating power is very critical. There's two ways you could do this. If you have a basic generator and resistor, is you have your voltage squared over your R, which is the voltage across this resistor. Or you have the current flowing into the resistor and you square times R. Either one of these works. You use whichever one you think is easier at that time during your circuit analysis. Okay. Next, we're going to have KVL or Kirchhoff's voltage law. This is basically loop analysis where you say, hey, there's one loop here. You got current flowing through it. It's all the same. And so all the voltages across this loop must equal 0. Now, this is a source right here. So V1 is putting voltage into the loop, and the other three elements are just either resistors or some inductor or capacitor. These are taking voltage out of the loop. So V1 is powering the circuit, and then V2 and V3 and V4 are absorbing the voltage. Okay, so V1 is equal to V2, V3, V4. Okay. Lastly, we look at Kirchhoff's current law. This is basically node analysis where you pick a node, which is right here, call this node A. The rule is current goes into the node has to equal all the current going out of the node, right? It's basic energy conservation. So in this case, I1 is going into the node. It must equal the sum of I2 and I3 coming out of the node. You'll see this all the time in the power system because loads are typically paralleled in the power system. So you'll have one major current coming in from the generator or the transmission system, and then it's going to be split among different feeders and loads, and you might have to calculate how much currents get split across each one of those loads. Okay. So that covers the very, very basics of circuitry. If some of those look unfamiliar, you might want to go back to your Circuits 1 book and just do a quick refresher, right? This is just here just to jog your memory. Next thing we can go to is a more complicated step of single phase power. So calculating power in circuits, you have S, apparent power, P, real power, and Q, reactive power. So let's go ahead and kind of go through each step to see how do we calculate power. So here we have Z1 element, right? We have a voltage source and current flowing through. So what's a quick and easy way to calculate apparent power S? So apparent power S, in this case, because it shares one node, which is directly tied to the voltage source, we can use voltage. So it's just going to be V1. Now we're going to use magnitudes because these could be phasors and they'll have phase angles. We don't want that. We just want the magnitude. So we got V1 squared over Z1 squared. No square on the bottom side. That's how you calculate the power. And this is going to be in volt-amperes, by the way. Okay. For apparent power S2, this one right here, Z2, we could calculate apparent power S. Here will be the same voltage because it's the same node on the top, divided by Z2 because this is the second element. And again, that's also in volt-amperes. Okay. So you can see here it's V squared over Z. Now, another way we could do this is think of the current loop. So we have current flowing through here. Again, this is I1. So how can we find apparent power S? For apparent power S here, we could just take the magnitude of the current and square it. I1 squared multiply by the magnitude of Z1 for Z1. And then for Z2, we could find apparent power S because it's a single looped circuit. The current is still the same, I1 squared times Z2. Okay. And these are also in NBA as well. Okay. Now, gets a little more trickier here is how do we solve for real power P? So P is going to be equal to, now let's look at the circuit. Real power P can only come from a resistive element right here, not the inductor. So you can ask yourself, well, what's the current flowing through? It's going to be hard to figure out because you got two elements. It's better to look at the voltage because it's directly connected to the source. So in this case here, I would just say, well, what's my magnitude of voltage is V1 squared, and divide by the resistor only. And that's going to give you your watts, real power. Okay. We could do this again for reactive power Q, right? So reactive power Q is going to come from the capacitor. So let's go ahead and just clean this up real quick. So reactive power always comes from either a capacitor or an inductor, never a resistor. Okay. Somebody ever asked you what's a reactive power resistor? It's always 0. Okay. So same thing we could think of. It's still the same voltage node here. So the voltage is still the same. So we could use the same voltage V1 squared, but this time we're going to divide by X of C. Okay. And this is going to be in VARs. Okay. Lastly, here we could solve for real power P. This time we're going to use a looped circuit. So here we have the same current flowing through everything, I1. So now let's figure out what's a real power P. P is going to be I squared, magnitude again, because that's a phasor, times your resistance. And remember, resistance is what real power dissipates out of. Okay, inductors have no real power. If somebody asks you what's the real power of inductor, it's always 0. Okay. And then we ask ourselves, well, what's the reactive power Q of the inductor, which is this one right here. Okay. Again, same loop circuit, same current. So we could say I1 squared times X of L. Okay. And this is going to be, again, in VARs, where powers and watts. Okay. So again, it's all about looking at a circuit, saying, do I know the voltage across the element? Do I know the current through the element? If you know either one of those and you know the impedance of the element, either J, X, L, R, or Z, you could figure out the power coming out of it. Okay. Okay. So let's kind of think about, what happens when we have more elements mixed in. I also want to introduce power factor calculations, because this is another way to describe the circuit, right? So here we have a voltage source. The only thing we know the power out the resistor. We know the reactive power out of the inductor. Notice it's negative because there's a capacitor. Capacitors produce negative reactive power. Now, how do we remember this? Well, you can always draw something called the power triangle. Okay, the power triangle is where you draw an x-axis vector, and that's always power P in the positive direction, pointing to the right. Reactive power Q is negative, so it's going to go down the page. This is going to be negative Q. Okay. And this is always not a 90-degree angle right here. Then, taking both of them together, you could find out the hypotenuse of the triangle. And that's going to be your S, apparent power. So this is what your power triangle looks like for a capacitive load. It's pointing downwards. Okay. Now, what's a power factor? Power factor can always be figured out by taking the real power and divide by the apparent power. So if you know those two, you got the power factor. Okay. Now, because it's a capacitor and it's negative VARs or negative Q, we have to say it's leading. Okay, a power factor, you must say if it's leading or lagging, otherwise it's incomplete. Okay. So just remember, capacitive on the circuit, leading power factor. Now we could go, let's look at the second circuit. Okay. Let's draw the power triangle and solve for power factor again. This time we have a inductor, which is positive Q. So let's again start with a real power P. It's always drawn in a straight line on the x-axis. This is positive P. Now, positive Q goes up the page, like so. And then the resulting vector is your apparent power S. Okay. Don't forget that there's this 90-degree phase shift here. I mean, 90-degree angle right there to complete the triangle. Now, power factor, again, same thing. We know P, we know S. We can find a power factor. And because it's a inductor, this is lagging. Now, some people ask, well, you know, I know P and Q, I don't know S off the page right here. Well, remember your trigonometry, this is a right angle. You could figure out S is equal to, or S squared is equal to P squared plus Q squared. Okay. So if you really know P, you can literally just say, well, S equals the square root of P squared plus Q squared. Okay. The power triangle is very, very powerful because it will remind you a lot of the formulas and how to kind of go between the three powers and help you find the power factor. Okay. Now, we could go the next level or next type of problem we'll see is, well, what happens if I just know the apparent power S and real power P, but then the Q is unknown? Okay, we know it's capacitive, but we don't know exact value Q. Can I figure it out? Yes. Again, same. I would always draw the power factor triangle. It solves a lot of questions. So let's go ahead and write out, again, positive P across the page. Again, reactive power is going down because it's a capacitive. We don't exactly know what it is, but we know it's going down the page because it's supposed to be negative. Okay, and then we have a apparent power S. Okay. Now, how do I know Q? Well, again, we look at our trigonometry. We can figure out Q is equal to the square root of S squared minus P squared. Now, if you ask me, so where do we get that? Well, on the right-hand side, we could go ahead and say, well, I know S equals P squared plus Q squared square root. We could do something very similar. If I want Q, we could rearrange this formula where Q squared is on one side and we throw P squared on the other. So it's S squared minus P squared. Okay. And then we could say, well, cancel out the square by square rooting both sides. Now we have S squared minus P squared. Okay. So again, power engineering is all about basic trigonometry here. Lastly, we could say, oh, well, I know S, I know Q. Well, what about P, right? Power off the resistor. Well, we don't know that yet, but we could figure it out. Again, power triangle. Now, resistors always absorb power. They don't produce power into the circuit, so they're always going to be positive. So we draw it on the right hand, draw the vector going to the right. This is, we don't know what it is, but we know it's positive. Now, we have an inductor, so our reactive power is going up the page because it's positive Q. And then the resulting vector is S. Okay. Again, right angle there. If I want to be technically accurate, I should put a right angle right here as well. Okay. All right. Different color pen. So how do I find P? Very similar to what we did here. We could go and just say, hey, well, P is just S squared minus Q squared. Okay. I'll let you go if you want to do your trig and rearrange your equation. You can figure out, but that's how you can figure out real power P when you have the other two. Okay. So just want to go through all this to show you power triangles are very, very powerful. This is expected. You know this by the back of your hand. That's when you start working. Okay. Now, let's go ahead and put this all together and try to do a review problem. Now, one way I want to do review problems is I'm not going to do everything for you. We're going to take about a 15-20 minute break, and you're going to do this on your own. Now, I'll give you a little, let me start you out real quick. First off is you have a standard source, you have a load, and you have a line. But we put this red line right here as a fault. So what's happening is a metal bar or these two wires fell off the power line and touched each other. So current will now flow out the source through this new wire or new contact path we made and go back to the source. So this is your new I fault circuit. Notice that this impedance right here is 0 ohms. It's a flat wire. So if you have 0 ohms, guess how much current is going to the load now? 0 amps. So in essence, you just cut out the entire load from the circuit. Now this is bad. A fault will damage equipment. It's going to burn the system down. Plus the load is not getting any power anymore. So if this is your house, you'd have a blackout. The entire reason why we have power protection and this entire course you're learning is to mitigate this exact problem and try to either stop it or change it as fast as possible. Okay. So why don't you go ahead, try to do your circuit analysis real quick. It's a single loop circuit with your impedance and your voltage source. Figure out your fault current and then figure out your apparent power, real power, and reactive power. Okay. Sorry, this should not be there. Okay, Q. Just don't forget that this is vectors now. So you have this angle 0 degrees and you have R and JX. Okay, so remember it's R plus JX. This will give you an idea. So let's take a 20-minute break. Stop the video right now. Work it out on your own. We'll come back and then work it out together and see where we're at. Okay, so thank you. All right, welcome back, everybody. So now we're going to go and work through this problem to kind of see what needs to be done. So the first thing we'll look at is, well, how do you figure out the fault current? So if you remember what we were talking about before is you would just take the low fault current and just pretty much use Ohm's law, right? So let's go ahead and see if we could push this over. Yes. So here, pulling from another sheet, is your fault current is going to be your voltage divided by the impedance of the circuit, basic Ohm's law. In this particular case, you have V source divided by R line plus JX line. Now, you go ahead and figure out the actual values for that is here. There you go. 2400 angle 0 voltage. So we got that right here. Divide by 0.1 R plus J 0.6 X. Now, you need a scientific calculator to figure this out because you can get a phase angle. So your phase angle will end up being, pull it across. 1 second. Oh, there we go. Right here. IF is equal to 3,945 amps at an angle of negative 80.5 degrees. You got a very big negative 80 angle because you have very big inductance and very small resistance. So remember, inductors cause a pretty big phase shift. So one telltale sign you have a fault on the system is, number one, you have high current. 4,000 amps, that's relatively high, right? That can burn down lines. Negative 80 degrees is on pretty big phase angle, so you're expecting this is fault territory. Okay, now let's talk about how to calculate your powers. You have your source power, apparent power of the circuit, the real power of the circuit, and reactive power of the circuit. Now, because the load is not connected, this is all dissipating across the line, R line, and JX line. So you notice the physical conductor is taking all the brunt of all the energy and the force, and you give it too much, it's going to physically burn down. This is why faults are bad. It burns down equipment. So how do we calculate all that? Well, it's just like the previous sheet shown, is you have S equal to V times I. right? So voltage times your current. Power is equal to I squared times R line because it's a single loop circuit, and Q equals I squared times X line because it's an inductor. We want to see how much current flow in the inductor to figure out our how much megavars or our reactive power. Now going down one by one, we can see the first one, apparent power S. This is equal to 2,400 volts times 3,945 amps, because that's a fault current flowing through the circuit. And that equals about 9.47 megavolt amperes, or we just call it MVA. Okay. So pretty high amount power going through the circuit. You're going to burn things down. Okay. Well, how much power is going through the conductor? Actual real power in megawatts. Okay. Huh. That kind of came off a little funny. Let's try to correct that real quick. Try and drag it over. Messed it up a little bit. Okay. So we have, move it over a little bit. We got, let's hotkey that equal sign in real quick. Let's try that color. I'm not sure if it will exactly match, but good enough. Yep. So here we have P equals I squared times R line. Again, we have 3,945 amps. Notice because in magnitudes, we don't have to put that phase angle in. Anytime you see this magnitude bars, you throw the phase angle away. Okay, so 3,945 squared times 0.1 ohms is about 1.55 megawatts. Okay. And lastly, let's look at the reactance of the line in megavars. So let's go and copy that. Oh, sorry. Oh, shoot. Let's make sure it's over here. Let's put the cursor here. And copy paste. There you go. Sorry about that. All right. So here Q is I squared times X line, where we have 3,945 amps squared times 0.6 ohms, because that's the reactance of the line. And this is equal to 9.34 megavars. So you can see that a fault is primarily megavars. So 9.34 megavars is a lot. You're going to burn things down at this point. So just kind of rehash and give you an idea. Remember, phase angles are a thing. So you have to keep track of your voltage phase angle, your current phase angle, and you have to calculate your powers based on your fault current and whatnot. Okay. Again, if this is all unfamiliar to you, I strongly suggest you go back to your Circuits 2 book, look up single phase power, review phasors, voltage phase angles, current phase angles, and single phase power. Okay, let's go ahead and move on. Next thing I want to talk about here is a three-phase system, right? Everything we talked about so far is single phase circuits. Realistically, in our power system, we run three phases. They're phases A, B, and C. Okay, so just remember A phase, B phase, and C phase. You can see this everywhere. Now, what do we consider a balanced positive sequence power system? Balance means the voltage magnitudes are all equal. Oof. Let me fix that. Voltage magnitudes are all equal. Okay. There are also 120 degrees phase separation between A, B, and C phase. Okay, again, this should be reviewed from EEE 141 and power system analysis, right? Three-phase voltages, all the same. A phase 0 degrees, B phase negative 120 degrees, C phase negative 240 degrees. Okay. What is also a positive sequence system? A positive sequence system means that A phase peaks first, and then B phase peaks, and then C phase peaks. Okay, so if you ever look at a oscilloscope, A phase comes first, then B phase, and C phase. So we call this ABC rotation. Okay, which is positive sequence rotation. And you have something called negative sequence rotation, which is ACB. Okay. Now we know basic voltages, balanced system, all voltages have to equal the same. They have the 120 degrees separation. We're positive rotation. Let's look at a three-wire diagram. So here we have three phases, A, B, and C. So we have a Y-connected source and a Y-connected load. So before we do anything complicated, I like to say, well, what's all the voltage and currents in the system, right? What do we have to pay attention to? Notice we have voltage between A phase and neutral. We also have a voltage between A phase and B phase. Okay, so we have two types of voltages. We could go VAN, VBN, VCN. Okay. We can also say we have, well, between A and B phase. So we have VAB. And then we have VBC and VCA. Okay. And then next, we got to look at currents. Well, we have A phase current IA, we got IB, we got IC, and because this is a four-wire system, we have IN. Okay, so we have IA, we have IB, we have IC. I'm going to put IN on the side because I'm going to say this is sometimes. Okay. If your system is perfectly balanced, IN will be 0. You won't see it. If it's a delta connected system with no neutral, IN will not be present. So this is a sometime thing. Okay. But definitely these first 9 ones, VAN, VBN, VCN, VAB, VBC, VCA, IBIC, that's in every power system known to man. Okay. So, you'll see these nonstop. All right. So we talked about three-phase ABC, voltage magnitudes are equal, 120 degrees separation. Well, what does that actually visually look like? Well, from the circuit, we could say, well, I know VAN, that's going to be equal to a voltage, right? This could be 12.47 kV. This would be 120 volts. This could be 480, 277. It could be something, right? But this will have an angle of 0 degrees. We're going to have VBN. It's going to have the exact same voltage, so the same voltage as the previous one, but this is going to be an angle negative 120 degrees, okay? And then VCN is going to be the same voltage with an angle of negative 240 degrees. So you can see they're always getting delayed by another 120 degrees. Now, some books and some people like to have shorthand and say, well, I don't like negative 240. I want to say positive 120 instead, but they're pretty much the same thing. Okay, you remember there's a rule you can always add 360 degrees, it means the same thing. So you could say negative 240 or positive 120, they both mean the same thing. Okay. I have a preference. I like to say negative 240 because it reminds me that, hey, we're always going negative 120 from A to B and then B to C. But I know plenty of people who do positive 120. Okay. Okay, so we know three phases A, B, C, all equal magnitudes, phase angle 120 degrees apart. All right. Now, unfortunately, in the power system, it gets a little confusing. We have VAN, and then we have VAB. They're not the same. They're different. Okay. Now, VAB is what we call line voltages. Typical numbers you'll see like 13.8 kV, maybe 12.47 kV. Okay? These are just like voltages that got standardized a long time ago. Don't ask me why you have all these round and little decimal places. That's just what was chosen 150 years ago. We had to deal with it. Okay. But VAB, this is typically line voltages. Okay. Now, how do we take VAB and equate it to VA? Okay, so maybe on the right hand side we'll say VAB is line voltages. Okay. So what's VAN? This is called a phase voltage. Okay. The big difference is phase voltage is from A phase to neutral, which is 0 usually. VAB is from A phase to B phase. Both of these are non-zero, so you're going to have to do some math. Okay. Now, let's go ahead and ask ourselves, well, what if I want to convert phase voltages to line voltages and back and forth? You're going to have to do this pretty often in the power system. And I'll tell you right now, even 20-year veteran engineers still get these confused, and so many mistakes and calculations made because they forget this conversion. So I want to go very slowly. I want everybody to understand it. Okay. Now, VAB, the subscripts A and B mean you take VAN. Sorry, let's even color code this. You take VAN and then you subtract VBN. Okay. That's the nomenclature we use. A to B means we subtract A from, so it's A minus B. So VAN minus VBN, because remember, voltages, potentials, there's always from one versus the other. So it's always one minus the other, okay? Or a comparison. So a question is we have VA minus VBN, how do we do that? Well, we could do it vectorially, right? So we could draw a vector, so we know VAN, okay, that's VAN. And that's some voltage at an angle of 0 degrees. Okay. We got VBN. I know that is going to go kind of down this way. This is VBN. And this is the angle. This is the same voltage, same magnitude because we're balanced, but this is negative 120 degrees. That's why it's drawn down to the left. There's a negative 120 degree phase shift here. Okay. Maybe it's worth noting this middle point right here. This is our neutral point N, which is 0. Now, I could vectorially subtract these two. So if you remember from physics, to subtract a vector, you take the tip and go tip to tip like this. But we kind of have to just slide it over, keep the same angle and the same facing. So just slide it over and kind of draw like a silhouette like this. Okay. It's the same phasor. We're just shifting it over the page. And then we could draw our resulting vector like so. And this will be VAB. Okay, so my opinion, at least, I'm a visual person. Maybe you are. If you ever get confused, draw out this vector, and then all the math makes sense. Because now this is a 30, 30, 120 triangle. So this is 30 degrees right here. This is also 30 degrees. And in between these two is 120 degrees. Okay, so first thing we could say, what's the difference between VAN and VBN, which is a 30-degree phase shift? Another question is what about the magnitudes? In a 30, 30, 120 isosceles triangle, the hypotenuse is always square root of 3 more than any of the other sides. You go back to 8th grade trig and argue with your teacher, is so. Okay, so we can say VAB will always be square root of 3 times more than VAN. Okay, remember VAB or the line voltage is always bigger than the phase voltage. So you should always multiply square root 3 in. Okay. And then don't forget, we should also add in a positive 30-degree phase shift. Okay, because you look at VAB, it's kind of up and to the right a little bit. So it's 30 degrees ahead of VAN. Okay. Now we could do the opposite. If we want VAN and we have VAB, so we're going backwards, we take VAB, which is the longer of the two vectors, we need to shorten it, so then we divide by square root of 3. Okay, and then if you look at VAN is kind of lagging, it's behind VAB because it's more down and to the right. So then we got to subtract 30. Oh, sorry, I'm using green right here. I like to color code it. So give me a sec. So this is square root of 3 because this is what we're doing. We're subtracting 30 degrees. Okay. So that's how you go between line and phase voltages. There's a square root 3 difference, and you're either adding or subtracting 30 degrees. I don't expect you to memorize this, but draw that vector, the triangle vector we just drew, and that can kind of give you an idea of you add or subtract 30 degrees, you multiply or divide by the square root of 3. Okay, very quick example we could look at. Give me VAN when I know VAB is 480 angle 0. So I know VAB is 480 angle 0 degrees. Well, I know VAN is the shorter of the two. So that I got to divide by square root of 3, right? And then I'll also have to subtract negative 30 degrees. This is going to equal to 277 angle negative 30 degrees. Okay. And right here is you have like a Y connected source. You can see where VAB is right here in the positive and negative terminals. So you could think about the two terminals up here and down here. That's VAB. And then you have VAN, which is between here and here. A and N. That's VAN, which is right here. Okay, so kind of just to give you a comparison. Even on this diagram, you can see VAB, in particular, this one is larger than the other two. That's why I chose this diagram, right? I like visual aids. We could go the other way. Let's say we want VAB and we have only VAN. We only have the phase voltage. Well, I know I have 277 at an angle of negative 30 degrees. So I know I must make it bigger. So I got to square root of 3 more. And then I got to also add 30 degrees into the circuit. Okay. So we go ahead. What's that number going to be? Well, it's going to be 480 at an angle of 0 degrees, which is back to the original step. So you can see this is a very basic conversion. Now, if you ever worked an internship or when you will start working in power engineering, you'll know that 480 and 277 are two numbers that go together because there's square root of 3 difference. So a lot of these numbers will have either a bigger number and a smaller one attached to each other. One's the line voltage, VAB, one's the phase voltage, VAN. Okay, and again, we use them interchangeably a lot in the power protection business. So again, it's very important that we keep track of which one we're using. Okay. Now, the last page, I want to kind of visualize everything put together. So we talked about different voltages, different currents, right? Let's go ahead and draw it vectorially because you'll see this a lot in reports. You'll see this a lot in computer programs and simulation programs you use, right? We like to see vectors. We like to see arrows all nice pointing in different directions. You know, visual aids are better than just numbers on a screen for most people. So let's go ahead and draw a vector of all these voltages. So I have VAN, that's 277 at an angle negative 20 degrees. So I'm only given that, right, in volts. Do I know VBN? Now remember, it's a balanced ABC rotation, 3-phase systems. Because balanced, I immediately know that the voltage is going to be the same for all 3 phases. A, B, and CN are all 277. Now the thing is each one will be negative 120 degrees lagging. So if I have negative 120 here, but I start with negative 240, it should be, sorry, I start with a negative 20 degree shift in A phase. I got to add or a negative 240 to it. So sorry, let me start over, mess it up. Let's just draw it out, right? So if I have negative 20 degrees for A phase, B phase is also a negative 120 degree more. So then our total should be negative 140 degrees. Okay, so we're just subtracting them out. So we got negative 140 degrees. Okay, and then C phase, we're going to do the same thing. We're going to put another negative 120 degrees. So we can put a negative 120 degrees for C phase. And that's going to be, let's do some math, negative 260 degrees. Okay, negative 260 degrees. Now, again, some people don't like negative 260 degrees. We could also call this positive 100 degrees as well. Either one works. I'll write negative 260 degrees for this one. Okay, so those are the 3 voltages for VA, VB, and VC. So let's go ahead and draw them out. So we have negative 120 degrees there. Oops. Negative 140 degrees, that's kind of like straight down is negative 90, so we're adding 50. So it'll be almost halfway between these two lines, kind of like that. Okay. So this is going to be VBN. And VCN, negative 260 is, you can almost again write it as positive 100 degrees, which is almost straight up. Going straight up the page is negative, positive 90 degrees. So it's a little bit more. So I'm going to say, let's get the artist in me out. Kind of like that. That's not that bad. Yes, this is VCN. So you can see three vectors kind of rotate a little bit, but because of negative 20 degree phase shift on A phase. So this one causes it to tilt just a little bit. But you can see that all three phasors are equally split apart. That's how you see a balanced system. So this is a balanced system with a phase shift. Okay. Now let's go ahead and do VAB, the line voltage, VAB, VBC, and VCA. So again, we're going to do a multiplied by square root of 3, and then we're going to add a 30-degree phase shift. Okay, that's because we're converting from a phase voltages to line voltages. Okay, so 277 times root 3 we did on the previous page. That's 480. Again, we know that is a balanced system, so all three voltages are going to be 480. Okay. Now, we just got to add 30 degrees. So negative 20 degrees plus 30 degrees, we're actually positive 10 degrees. Okay. And then we could go through all three of them. So there's two ways. We could either add 30 degrees to each of them, or we could say, well, the next one over here is just negative 120 degrees off, right? Because they're still balanced. Either one works. So if I put a negative 120 degrees plus positive 10 degrees, it's actually negative 110. Well, if we also go from negative 140 and add 30 degrees, we'll also get negative 110 as well. So it's the same way either one. Okay, again, the same thing. We put a negative 120 degree phase between these two. This can be negative 230. Or we could add 360 to this and cause positive 130 degrees. Either one works. Okay. Now, let's go ahead and draw them out. So here, 480 is obviously longer than 277, so it's going to be bigger. Plus 10 degrees is not much. So it's actually kind of like that. Okay, this is VAB. And remember, this is positive 30 degrees between right here. Okay. Next is negative 110 degrees. So again, it's 30 degrees off of VBN. So we'll be ahead by 30 degrees, kind of like that. Okay, that's VBC. And then lastly, positive 130 degrees. Again, we'll call this about, let's see, 130. This is 90. This is 180. It's kind of halfway in between. Let's draw it kind of like that. Yeah. Okay. That came out decent enough. So again, you can see there's that 30-degree phase shift between all three of those. And now if you look at it from a large scale view, look at the green arrows. The phase angle is off a little bit, but it's again 3 phasors perfectly aligned, 120 degrees apart. So there's a lot of symmetry involved in this drawing. So this is why a balanced system is so easy, because once you know the first VAN, you can literally calculate all the other voltages in the circuit. So all we really need to know is just one voltage to get all the rest of them. Okay. So I think this is a call for today. So thank you for showing up and listening. So if any of this seems unfamiliar or you need a refresher course, please go look at some rest material, contact me. We'll try to get you straight because we're going to be moving forward. So thank you very much, everybody. Have a good day.